Hello everyone, welcome back to channel. Welcome back to CFD College. I'm Ashkan, and as you may know, this is the last video of Fluid Mechanics 1 course. I hope you've enjoyed previous videos and tutorials. I really wanted to help you understand this course and get a good grade. So I hope you have found these videos useful for you, and please introduce us to your friends who will take this course in future semesters, so they can enjoy these videos too and learn better this course. So let's jump to the assignment, to problems. I think we have 10 or 11 problems in the last assignment F, regarding flow in pipes, and I'm going to solve them for you in this video. If you would like to work or pursue your education in fluid mechanics, numerical simulations, CFD, ANSYS Fluent, or something like this, you can subscribe the channel. You can learn many useful tips and tutorials and courses. You can find various courses related to CFD in this channel, and I think those videos would be helpful for you too if you would like to learn numerical simulations in the field of fluid mechanics. So this is the last assignment, the last video. Assignment F, as I mentioned, it is related to flow in pipes. The first one, problem 14 of chapter 8. Water flows in a constant diameter pipe. As you know, when the diameter of the pipe is constant, D1 for example equals D2, it means that area 1 equals area 2, and since Q, flow rate, is constant, actually Q1 equals Q2, it means that V1 equals V2. So this is the meaning of this statement: constant diameter pipe. With the following conditions measured at the section A, we have pressure, we have elevation, and also at section B we have these info. Is the flow from A to B or from B to A? Well, here we should find the direction of the flow. So for example, if this is the pipe, since ZB is greater than Z1, the elevation, this should be point B, this should be point or section A, and we want to find the flow direction. As you know, when you have a fluid flow, you need to use energy equation, which is PA or P1, it doesn't matter, over gamma plus VA square over 2G plus ZA equals PB over gamma plus VB square over 2G plus ZB. And as you may know, I always told you, you should follow the flow. By that I mean, if, for example, assume that the flow direction is from left to right. If this was the flow direction, it means that you should have section A at the left hand side and section B at the right hand side. Why? Because we should place HL, the head loss, at the destination side, the right hand side. And of course, if we have turbine, we should place it here, and if we have a pump, we should place at the left hand side. Or if the flow is from right to left, then you should place these in a reverse manner. So we should have HL and HT near the destination, which is section A, and head of the pump near the beginning point of the flow, the start point of the flow. Okay, so in this problem, since we don't know which one is the flow direction, we should assume one direction and then solve the problem. So if we assume this is the flow direction, so we should use this type of energy equation, and since there is no pump and turbine, these terms are gone. So what we have is PA over gamma plus VA square over 2G plus ZA equals PB over gamma plus VB square over 2G plus ZB plus HL. Since the diameter is constant, we know that VA equals VB, so these terms are gone, and we have pressure and elevation at point A and B. So from this you can understand that HL equals PA over gamma minus PB over gamma plus ZA minus Z. And if you know, HL is always a positive value. It can be zero if we neglect the major losses. Remember, HL is a major loss, not a minor loss. So HL should be equal or greater than 0. So you should calculate HL and check this whether the HL is greater than 0 or is a negative value. If it was a negative value, that means that the assumption would be wrong. Okay, so HL equals PA 32.4 pounds per inch square psi minus 68.2 pounds per inch square. Don't forget to convert it to feet. Convert actually inch square to feet square. Gamma of water is 62.4 pounds per cubic feet plus ZA 56.8 feet minus ZB 68.2. Oh, sorry. This is the pressure is 29.7. Sorry. Feet. And if you calculate it, you will find that HL equals minus 5.17 feet, which is a negative value and it's impossible. So the assumption we made at the beginning was wrong. So the flow direction is from right to left, from B to A. Next question, problem number 19. It's so easy. A fluid flow through a horizontal 1-inch diameter pipe. So the pipe is horizontal, the diameter is 1 inches, and 0.1, I think this should be 0.1. Yes, it's 0.1. We know the Reynolds number, which is 1500. When the Reynolds number is 1500, the head loss over a 20 feet length, so L is 20 feet. We know the head loss, HL equals 6.4 feet. Determine the fluid velocity. It's so easy. As you know, HL equals FL over D V square over 2G. We should find F first and velocity. So we know that Reynolds number is rho V D over mu, or rho V D over mu. But in this problem, we know the value, so it's smaller than 2100, which is the critical Reynolds number. So the flow is laminar, so F equals 64 over Reynolds number, so F equals 0.0427. So by having the Reynolds number, we can find F, and now HL 6.4 feet equals F 0.0427. I'm writing this formula. Actually, I'm putting the values inside it. L is 20 feet. Diameter is 0.1 over 12 feet. Velocity square over 2G, 2 times 32.2 feet per second square. And from this, you can find velocity is 2.01 feet per second. Okay, as I mentioned, it was really easy problem. Next, problem number 23. A 3-inch schedule 40 commercial steel pipe. Okay, now we have diameter and the material with actual inside diameter of this one. So this is the actual inside diameter. Carries this oil. This is a specific oil. The temperature SAE 40, crankcase oil at the rate of 6 gallons per minute. So we have the flow rate also. The oil specific gravity SG is 0.89. So we know flow rate 6 gallon per minute. We know SG of the oil 0.89. The viscosity, so we have the viscosity of this this particular oil. Mu is 6.6 10 to minus 7 pound second per feet square. For the same pressure drop, what must the new pipe size be to carry the oil at this flow rate? So this is the flow rate, and we want to know if the flow rate increases to 10.7 gallons per minute, and we want to have the same pressure drop, so delta P1 equals delta P2. What must be the new pipe size? So we should find the new diameter, D2. Let's call this Q1, Q2, delta P1, delta P2, D2. Since we have D1, should find D2. while we know D1 equals 3.068 inches. Okay guys, so we have a pipe flow and we want to find the new diameter with this new condition. So first thing, we should find delta P. Without having the pressure drop, we can't do anything. So since we have a fluid flow in pipe, we should use energy equation. So consider, for example, this is the pipe. Here is 0.1, here is 0.2. This is length of the tube. And if we want to find pressure drop, P1 over gamma, and consider this flow direction. Plus V1 square over 2G plus Z1 equals P2 over gamma. There is no pump or turbine. Plus V2 square over 2G plus Z2 plus HL. And I think I have to change the subscription. So here is A, here is B, because we had 1 and 2. So this is A, this is A, B, B, and B. Okay, so since the diameter is fixed, you know that since D1 equals, since dA equals dB, it means that VA equals VB. So these terms are gone. So from this, you know that you will find out that PA minus PB over gamma equals ZB minus ZA plus HL. So if you multiply both sides by gamma, delta P1, delta P equals PA minus PB equals gamma times ZB minus ZA plus gamma times HL. As you know, this is F L over D V2 over 2G. If you multiply this by gamma, gamma is rho G, you will have FL over D V rho V square divided by 2. So in conditions 1 and 2, everything is the same except diameter. So L is the same. So L1 equals L2. Friction. We should consider friction. Can we consider friction constant in these two situations? No. Why? Because friction depends on the Reynolds number, so the diameter is important, the velocity is important. So we should find a relationship between F1 and F2. Diameter, we should find diameter, so it's out of option. Density is fixed, density is constant, so rho 1 equals rho 2, and also the viscosity, and ZB and ZA, they are constant, so ZA1 equals ZA2, ZB1 equals ZB2. So this is the expression for delta P. So for delta P1, we will have gamma, which is fixed, ZB1 minus ZA1 plus F1 L over D1 rho V1 square over 2. And for delta P2, we have gamma ZB2 minus ZA2 plus F2 L over D2 rho V2 square over 2. So if dP1 equals dP2, these terms are equal, so they are gone. So we know that F1, it means that F1 L over D1 rho V1 square over 2 equals F2 L over D2 rho V2 square over 2. Since L and rho are fixed, it means that F1 V1 square over D1 equals F2 V2 square over 2. So this is the expression we derived from energy equation. The next step is to find F, something for F. We need that. So to find F, as you know, first we should find whether we have turbulent flow or laminar flow. So we should calculate Reynolds number. Reynolds number equals rho Vd over mu, or 4 rho q over pi d mu. It's not difficult to get this. You just need to replace velocity by q over, this one. This velocity equals q over area. Area is 4q over pi d square. Pi d square divided by 4, so 4 goes into the numerator times q. Now we can calculate Reynolds number at both scenarios. So Reynolds number at first situation equals 4 times rho 0.89 Sg times density 1.94 slugs per cubic feet. This is Sg times rho of water. And the flow rate, 6 gallons per minute. And you should convert gallons per minute to cubic feet per second. So 1 cubic feet per second equals 448.8 gallons per minute. And the slug conversion, so pounds second square, slugs feet. So 1 slug equals 1 pounds second square over feet. And here we have pi diameter d1. We have that 3.068 over 12 feet, and mu 6.6 10 to minus 7 pounds second per inch square. So it was an inch square or feet square. So it should be in inch square. Inch square. Okay. And then we have to convert inch square to feet square. Okay, so the Reynolds number in the first situation equals 1210, which is smaller than critical Reynolds number. So we have laminar flow. So F equals 64 per Reynolds. And you can find it. So F1 equals 64 over Reynolds number equals 64 divided by VD over nu, or 64 we should use Q here, 64. So you should use this one again, which is equal to V. Therefore F equals 64 pi d nu over Q. This is D1 and Q1. This is friction factor for the first situation. The Reynolds number for the second situation, we don't have diameter. We have rho Q mu, but we don't have D2. So what should we do? We should assume that the flow is laminar. So we should use this assumption, assuming that the flow is laminar. So if the flow is laminar, we should use this formula like this one. F2 equals 64 pi d2 nu over q2. And we solve the problem. After that, in the end, we should check this assumption, whether it's true or not. How? When we have d2, we can calculate Reynolds number and check the assumption. So now we have F2. Where were we? Here, equation A. So from equation 1, we have to replace velocity by this important expression. First, I think we should do that. So if we do that, equation 1 will be this one. So F1 Q1 square over D1 to power 5 equals F2 Q2 square over D2 to power 5. And now we have expression for F1 and F2, which is 64 pi D2 nu over Q2. So from this, you can find that first D2 to the power 5 that we want to find equals F1 Q1 square over F2 Q2 square over F1 Q1 square times D1 to power 5. And if we replace F1 and F2, we would have D2 to power 5 equals 16 pi d2 nu over q2. This is f2 times q2 square over 16 pi d1 nu over q1, which is f1 times q1 square times d1 to power 5. So again, kinematic viscosity is fixed and these terms are gone. So we will have d2 to power 5 equals let me check it. d2 times q2 over d1 times q1 times d1 to power 5. So d2 equals d2 to power 4 equals q2 over q1 times d1 to power 4. And now you have everything that then you can find d2. How? d2 to power 4 equals q2 10.7 gallons per minute over 6 gallons per minute times 3.068 inches to power 4. So d2 equals 3.55 inches. This is d2. So the actual pipe diameter, when you have a 3.5 inch pipe, is 3.548 inches. This is the inner diameter of the pipe. So we have the diameters. We just need to check the Reynolds number. You know the calculations. It's like what we did here. So I just check it. Reynolds number in second situation equals 4 rho q2 pi d2 mu, and if you calculate it, you will find that it's equal to 1860. So it's below critical Reynolds number and we are still in laminar region. So the assumption was correct and we don't need to change anything. And that's it. Now, oh sorry, I made a mistake. The Reynolds number equals 254. Or no, it was correct. 1860. Okay. So this was this problem. It was a bit tricky, I think. It was, when you don't have one info, for example velocity or diameter, the problem is a bit tricky. This problem I don't want to solve it because this is similar to the previous one, but here we don't have two flow rates. Actually, Q1 is also equal to Q2, so the flow rates are equal. It's simpler than the previous one. And the other difference is here delta P 1/2 the delta. So delta P2 should be 1/2 times delta P1. So this is the only difference, it's actually easier. You need to add this one, and wherever you had Q1 and Q2, they're equal, so you can cancel them. So I don't want to solve this problem. It's quiet. It's completely similar to the previous one. Next problem number 38. Problem number 38. Water flows through a horizontal pipe. The diameter is 60 millimeters, so the pipe is horizontal and the diameter is 60 millimeters. Galvanized iron. You know why it's important? Because you need to know the roughness from the table in the book. I think I mentioned the table in the previous video in tutorial 12. From that table for galvanized iron, you will see that epsilon roughness actually equals 0.15 millimeters. We know the flow rate at a rate of this, so flow rate is 0.02 cubic meters per second. If the pressure drop is 135, so if this is the flow rate, here is section 1, section 2, per 10 meters of pipe, so the length is L is 10 meters, then the pressure drop P1 minus P2 equals 135 kilopascal. Do you think this pipe is a new pipe, an old pipe with a somewhat increased roughness due to aging, or a very old pipe that is partially clogged by deposits? Okay, so we should find friction factor, and then we can decide whether it's new or old or very old. So this is a horizontal pipe. We have a fluid flow, so P1 over gamma plus V1 square over 2G plus Z1 equals P2 over gamma plus V2 square over 2G plus C2 plus head loss. Since the pipe is horizontal, we know that the diameter is fixed, so V1 equals V2, Z1 equals Z2. So this is gone, and these ones. Okay, so P1 over gamma minus P2 over gamma equals HLFL over D V square over 2G. Actually, for horizontal pipes, you can find delta P as FL over D rho V square over 2. So we have everything, we can calculate F. Delta P is 135 10 to power 3 Newton per meter square equals F. We don't have that. Length, which is 10 meters, diameter 0.06 meters times rho, 999 kilograms per cubic meter. So we have to find velocity, and it's easy because we know the flow rate Q and the diameter. So Q equals A times V. So velocity equals Q 0.02 cubic meters per second over area pi d square 0.06 divided by 12. Don't forget that. So velocity equals 7.07 meters per second. So we have the velocity now, 7.07. Okay, 7.07 meters per second s square over 2. So friction can be found from this 0.0324. This is the friction that we calculated. This is the actual friction we have in our pipe. So now we should calculate the friction from the Moody chart to see whether it's equal to this friction or less than this friction, because the pipes, the lines actually that you have on Moody diagram shows you if the pipe is new, this would be friction factor. So first let me find Reynolds number, whether to see whether we have laminar flow or turbulent flow. Reynolds number equals Vd over nu. Velocity equals 7.07 meters per second. Diameter 0.06 meters, and nu 1.12 10 to minus 6 square meter over second. So Reynolds number equals 3.79 10 to power 5. It's greater than critical Reynolds, so we have turbulent flow. So when we have a turbulent flow, we need Reynolds number and dimensionless roughness. Epsilon over d, we know epsilon 0.15 millimeters divided by diameter 60 millimeters equals 2.5 10 to minus 3. So this is the roughness, and we have the Reynolds number, so you can go to Moody chart and find the friction. So give me a second to bring up the Moody diagram. Okay, here you can see the Moody diagram. Let me do this. Okay, and so we had Reynolds number of 3.8 10 to power 5, somewhere here, for example near this line. And for the relative roughness, we had 2.5 10 to minus 3, somewhere here. Here, this line. So if you see this, we are here, somewhere here, and this point shows us this friction factor. So friction factor for this Reynolds number, for this relative roughness, is around 0.0255, but what we got was 0.0324. It's much greater than this one. So it is too much actually. Now let's check with this. At this Reynolds number, let's find this friction, which is here, for example, somewhere here. And if you see, it means that the epsilon over d should be around this 0.006, but the epsilon over d in our calculations was 2.5 10 to minus 3. So it's greater than twice actually. So it means that this pipe is too old. It's an old pipe, it's a very old pipe with roughness, with a higher roughness. So let me go back this card. Now you know how to work with Moody diagram. I wanted to show you. So since, let me write it down. So from by this Reynolds number 3.79 10 to power 5 and epsilon d equals 2.5 10 to minus 3. From Moody diagram we found that f should be 0.0255, which is much smaller than 0.0324. And then when we go with this information, Reynolds number equals 3.79 10 to power 5 and friction of 0.0325. we found that from Moody diagram epsilon over d is somewhere here. So it means that this is an old pipe because we have twice roughness. When we have a clogged pipe, the roughness is much higher. So when, for example, we have a pipe with diameter of 60 millimeters, if the pipe is clogged, for example, the epsilon over d should be near 0.1 or something. So it's smaller than 0.1. So the answer is B, an old pipe, not a very old pipe. I think I mentioned a very old pipe, but it's not true. It's just an old pipe. Okay, let's see what we have in the next problem. Problem number 39. Water flows at a rate of 10 gallons per minute. So we have flow rate 10 gallons per minute in a new horizontal 0.75 inch diameter. So we have the diameter 0.75 inches galvanized iron. So we know epsilon equals epsilon for this pipe equals 0.0005 feet. Remember, it was 0.15 millimeters, but here we are working with, we should work with feet. And determine the pressure gradient delta P over L along the pipe. As you know, and what you have seen in the previous problem, I told you pressure drop for horizontal pipe equals F L over D rho V square over 2. So delta P over L equals F rho V square over 2 times D. Okay, so we need friction, we need the velocity, we should calculate it. We have the flow rate, it's 10 gallons per minute. We should multiply this by every 1 gallon equals 1728 cubic inch, and Every 231 cubic inch equals, sorry, this is 1 cubic feet. Here is 1 gallon. So every gallon equals 231 cubic inch. Every 1728 cubic inch equals 1 cubic feet. And what else? Every 1 minute equals 60 seconds. Now we have the flow rate in cubic feet per second, 0.0223 cubic feet per second. So we can calculate velocity. It's equal to Q over A, 0.0223 cubic feet per second over pi over 4. We have the diameter divided by 12 feet square. So velocity equals 7.27 feet per second. So we have to calculate Reynolds number to see whether we have turbulent flow or laminar flow. Rho Vd over nu, velocity is 7.27 feet per second. Diameter is 0.75 over 12 feet. Nu is 1.21 10 to minus 5 feet square over second. So Reynolds number equals 3.76 10 to power 4. It's greater than critical Reynolds number, so we have turbulent flow. So we need epsilon over d, 0.0005 feet divided by d, 0.75 over 12 feet equals 0.008. So now if you go to Moody Chart with this Reynolds number and epsilon over d, just like what I did in the previous problem, you will find that friction factor equals 0.037. And now you can find the answer. Delta P over L equals F, 0.037. Density 1.94 slugs per cubic feet. V 7.27 feet per second square divided by 2 times diameter. It equals, so delta P over L equals 330.4 pounds per cubic feet. And if you multiply it by 1 feet square equals 144 inches square, you will have that 0.021, okay, no, 211 psi per feet would be the pressure lost per length for this problem. Let's go to the next one. Problem number 43. Gasoline flows in a smooth pipe. A smooth pipe means epsilon is 0 and you need to use this line, the lowest line. If you see here, you can see a smooth pipe, so you should use that line if you had turbulent flow. We have the diameter of the pipe, flow rate. If it were possible to prevent turbulence from occurring, okay, what would be the ratio of the head loss for the actual turbulent flow compared to that if it were laminar flow? So actually in this problem we have to calculate head loss in turbulent flow and laminar flow, and we have to compare them. And it's not difficult because you know HL, the head loss, equals FL over D V square over 2G. So we have two different head losses. So HL for laminar flow equals FL times FL means friction factor in laminar flow, L over D V square over 2G, and for the turbulent flow it would be friction factor of the turbulent flow, L over D V square over 2 G. So basically length, diameter, velocity, gravity, these are the same. So HLT over HL, because it's not an actual situation. We know, I think we know the flow is turbulent, but we have to assume it's laminar, so velocity doesn't change in these two situations, equals FT over FL. So we just need to find friction factor. So let's find velocity first and then Reynolds number. Okay, so what will we know? For the gasoline, we know that density equals 680 kilograms per cubic meter, and viscosity of this fluid is 3.1 10 to minus 4 Newton second per square meter. And velocity, which should be equal in both laminar and turbulent flows, is Q over A. We know Q 0.001 cubic meters per second divided by area, pi over 4, and diameter is 0.04 meters square. So V equals 0.796 meters per second. So now we can calculate Reynolds number, which is equal to rho V D over mu. You know velocity, diameter, and the density and viscosity. So it's equal to 6.98 10 to minus 4. Okay, so if we have laminar flow, we know that FL equals 64 over Reynolds number, so you can calculate it. It equals 9.16 10 to minus 4. And if we have a turbulent flow by this Reynolds number, and we need epsilon, oh no, we don't need epsilon over D, with this Reynolds number and a smooth pipe line, you can find that FT equals 0.0192. So HL in turbulent flow over HL in laminar flow equals 0.192 over 9.16 10 to minus 4 So HLT over HL laminar equals 21. This is the ratio if you consider the flow is laminar, but as you saw, we know it's not laminar, it's actually turbulent. So this problem number 73, at the ski resort, water at 40 degrees Fahrenheit is pumped through a fringe diameter 2,000 feet long steel pipe from a pond at an elevation of 4,286 feet to a snowmaking machine at an elevation of 4,623 feet at a rate of 0.26 cubic feet per second. So basically we are pumping the water, so from this elevation to here we are pumping the water. So here is 0.1, here is 0.2. Neglect the minor losses, okay? Oh, here we were here. If it's necessary to maintain a pressure of 180 psi at this snowmaking machine, so actually we know pressure at 0.2, 180 psi. Determine the horsepower added to water by the pump. So we should find W dot of the pump, the net power of the pump. So it's not difficult. P1, as you know, we should use energy equation, P1 over gamma plus V1 square over 2G plus Z1 plus HP. Here we have a pump in between, equals P2 over gamma plus V2 square over 2G plus Z2 plus head loss. Remember, head loss is not a minor loss, it's a major loss. So never neglect that. What do we know? We know that P1 is atmospheric pressure, so P1 equals 0. We know Z1 and Z2. Z1 equals 4286 feet, while Z2 equals 4623 feet. We know P2 180 psi, and also we know that V1 equals 0 because it's a free surface. Okay, so this term is 0, this term is 0, we have Z1, we have Z2, we have P2. We should find V2 because we want to find HP, and we also know that HL equals FL over D V square over 2G. We know the length 2,000 feet, the diameter 3 inches, and we should find velocity by flow rate. So V2 equals V is this velocity inside the pipe, equals Q over pi over 4 times D square. We have everything, 0.26 cubic feet per second over pi over 4 times 3 over 12 feet. So velocity is 5.3 feet per second. So this is the velocity. You can, by having the velocity, you can calculate Reynolds number, Vd over nu, 5.3 feet per second, 3 over 12 feet over nu, 1.664 10 to minus 5. So the Reynolds number equals 7.96. Don't worry about kinematic viscosity, density, or dynamic viscosity. They should be given to you at the exam. Times 10 to power 4, it's greater than critical Reynolds number. So we have turbulent flow. So we need epsilon over d. The pipe is made of steel. So epsilon equals 0.00015 feet. So epsilon over d, you have diameter, equals 6 10 to minus 4. With this Reynolds number and this epsilon over d, you should go to the Moody diagram. So with Reynolds number and calculated epsilon over d from Moody diagram, you will find that F friction factor equals 0.0212. Actually, I know it can't be so accurate from that chart, but in the exam it's okay if you calculate it near the correct value. Okay, so now we have everything. So we can calculate HP. HP equals P2 over gamma plus Z2 plus plus V2 square over 2G plus Z2 minus Z1 plus FL over D V square over 2G. Remember that V equals V2 because the diameter of the pipe is constant. So here we have V2. So HP equals P2 over gamma plus Z2 minus Z1 plus, if we factor out V square over 2G, we would have 1 plus FL over D. And now you have everything. You have the pressure. I just write down the values. 180 pounds per inch square. You should multiply this by 144 inches square over feet square. Gamma is 62.4 pounds per cubic feet. And what else? Z1 is noun, Z2 is noun. You know velocity, you know F. L is 2000 feet. Diameter is 3 over 12 feet. Gravity is 32.2 feet per second square. And now you can find HP. It equals 827 feet. But you have to find the net power of the pump. So W dot of the pump equals gamma Q times HP. So gamma is 62.4 pounds per cubic feet. Q is 0.26 cubic feet per second times 827 feet equals 13,420 pound feet per second. And if you divide it by 550, because every 550 feet pound per second equals 1 horsepower. It equals 24.4 horsepower. And I think we have 2 other problems. Yes. Problem number 86. Water flows from a nozzle attached to the spray tank. This is the nozzle. shown in the figure below. Determine the flow rate. So we should find the flow rate. If the loss coefficient for the nozzle based on upstream conditions, so it's a new problem. Here we have the loss coefficient. As I mentioned many times, we have minor losses and major losses. Major loss, which is, for example, HL, FL over D, V square over 2G, and we have minor losses. For example, in a bend, or when you have a sudden expansion or contraction, or when you have a nozzle. In these situations, you should have the loss coefficient, because here the loss, I don't know, maybe, for example, we show it with, this is, for example, HL. This is HL with capital and lowercase l. It's equal to K times V square over 2G. K is the loss coefficient. V is velocity, and most of the times it's based on upstream condition. You know, fluid flows from upstream to downstream, and when you are told that the loss coefficient for the nozzle based on upstream condition is 0.75, it means that the loss coefficient is 0.75, and this velocity is the upstream velocity. So, for example, if you have a sudden expansion with this situation, you know, here is the flow, the upstream is here, so this velocity is velocity of the flow in the smaller pipe. If you had solid contraction based on the upstream, you should use velocity in the larger pipe. So in this problem, when we have this nozzle and we are told that there is a loss coefficient for the nozzle, it means that we have a minor loss, K V square over 2G, and we have the loss coefficient. Since it's based on upstream, it means the upstream of this nozzle is this tube. So this velocity is velocity inside pipe. Okay, so it's good. Now I think you know what does it mean. And the friction factor for the rough house is 0.11. So in this problem, we know KL. We use KL for this, sorry. KL is 0.75 and F is 0.11, the friction factor. So it's easy. We have pressure, the air pressure actually. Here the air pressure is pressure on this surface. So here we have 0.1 and here we have the exit 0.2. So this we should use these key points because we have velocity and pressure. We have some info about them. So P1 over gamma plus V1 square over 2G plus Z1, there is no pump, equals P2 over gamma plus V2 square over 2G plus Z2 plus both losses, minor losses and major losses. So plus F L over D V square over 2G plus KL V square over 2G. I should make it thinner. Okay. So as you know, this velocity is the velocity of the flow inside the pipe. The same is true for this one, because we know that we should calculate based on upstream condition, and F is also friction for this tube. So what do we know? We know that pressure at point 1 equals 150 kilopascal. We know velocity at point 1 is 0. It's a surface, free surface actually. And what else do we know? Z1 is 0.8 meters. For point 2, we know pressure at point 2 is atmospheric, it's 0. We should calculate velocity at point 2, and remember that here V2 is not equal to V. V is velocity inside the pipe with a diameter of 15 millimeters, but the nozzle diameter is 7.5 millimeters. It's half of this. So V2 is greater than V. Why? Because the nozzle diameter is half of the diameter of the pipe. These are important. Be careful. And what else do we know? Oh, Z2. We can calculate Z2. It's length of the tube times sine of 40 degrees equals 1.22 meters. You know L, 1.9, and the angle. Okay, now just let us find velocity. V2 equals Q over A2. Q is we should find it. Okay. So Q over A2. And V is Q over A, the area of the pipe. So for example, AP. And what else do we know? We know that diameter of the pipe is 2 times diameter of the nozzle. So here instead of nozzle I can write down D N or D2. So from these we can understand that V2 over V equals area of the pipe over area of the nozzle equals pi over 4 dp square divided by pi over 4 d2 square. So V2 over V equals 4. 2 to the power 2 equals 4. So V2 equals 4V. And now we should put the values in energy equation. P1, 150, 10 to power 3 Newton per square meter. Gamma of water, 9.8, 10 to power 3 Newton per cubic meters, plus Z1 equals P2 is 0, And okay, we have Z2 1.22 meters plus V2 square over 2G equals 16 V square over 2G. So if we factor out V square over 2G, if we factor out this, we will have, let me write down it here, V2 over 2G, F L over D plus KL plus 16 plus 16 plus F 0.11, length 1.9, diameter 0.015 meters, L over D plus KL 0.75 times V square over 2G. So from this you can find velocity 3.09 meters per second, and by having the velocity you can find Q equals V times area. Don't forget that this V is velocity inside the pipe, not at the exit of the nozzle. So pi over 4 0.015 meters square times 3.09 meters per second. So Q equals 5.46 10 to minus 4 cubic meters per second. This is Q. So let's solve the last problem. Yes, this is the last problem. Problem number 103. Determine the diameter of a steel pipe that is to carry 2000, so we know flow rate, 2000 gallons per minute of gasoline. So gasoline, the density is 1.32 slugs per cubic feet, and viscosity for gasoline is 6.5 10 to minus 6 pounds second per feet square. With a pressure drop, so we have the pressure drop delta P of 5 psi per 100 feet of a horizontal pipe. So delta P is 5 psi and length is 100 feet. The pipe is horizontal, so since the diameter is fixed and the pipe is horizontal, you know that delta P equals F L over D rho V square divided by 2. Okay, sorry. Since this is a horizontal pipe with a constant diameter, if the diameter wasn't fixed, you have to write down the energy equation. Okay, so first we need to find velocity, but we can't because we don't have the diameter. So this problem is kind of trial and error problem, like I think 2 of them we have in the previous video, tutorial 12. It's like that. So okay, let's solve it. Velocity equals Q over A. Q is 2000 gallons per minute. Every 1 every 231 inches square is cubic inch is 1 gallon, and every 1 cubic feet is 1728 cubic inches, and 1 minute equals 60 seconds. Divided by area, pi over 4 times d square. So velocity equals 5.67 over d square. If you remember, we need to find some expressions. Okay, now we have velocity. Let's put it in star equation. So delta P, 5 psi, pounds per inches square, times 144 inches square over feet square, equals F, you don't have it, length of the tube 100 feet, diameter of the tube, density 1.32 slugs per cubic feet, times V square over 2, so 5.67 over d square divided by 2. So from this you can find that d equals 1.24 times friction to the power of 1 over 5. So this is the first equation. The second one is Reynolds. It's pretty similar actually. Rho Vd over mu, you know density, diameter is unknown, and velocity you should use this one, and you have the viscosity. So Reynolds number equals 1.15 10 to 6 over d. And so we should consider we are in turbulent flow. There is, most of the flows in nature and in our lives are turbulent. So epsilon over d is also a function of diameter. For the steel, epsilon equals 0.00015 E over d. So this is equation number 2. So as you know, in these kinds of problems, we have to make an assumption for friction factor, and always start with this one, 0.02. Having the friction, using equation 1, you can find diameter. So diameter equals 0.567 feet, and let's call it equation 3. Having the diameter, using equation 2, you can find Reynolds number 2.03 10 to power 6. As you know, we are in turbulent flow region, and using equation 3, epsilon over d equals 0.000265. Now you should go to Moody chart. You have Reynolds number and epsilon over d, so you can find new f. F equals 0.018148, and which is clear that it's not equal to 0.02. So you should try this way again and again until you reach a closed value. So now we have a new f. It's not an assumption yet. F is 0. It's not an assumption because we calculated this f. So if f equals 0.0148, using equation 1 you can find diameter 0.534 feet. Then using equation 2 you can find Reynolds number 2.15 10 to 6. Using equation 3 you can find epsilon over d 0.000281. Using Moody diagram you can find f equals 0.015. it's near 0.018148. So we can consider this f our final friction. So f equals 0.015. So using equation 1 you can find diameter d equals 0.535 feet, and this is the final answer to this question. So this is the end of this video, end of this playlist, end of this series of videos on Fluid Mechanics 1. I hope you've enjoyed it. I hope you have learned something from me, from solving these problems. If so, I'm happy. That's all I needed. That's all I wanted from the beginning. So please share these videos with your friends in future semesters, and please you can subscribe the channel. I have lots of useful videos. You can enjoy them if you are working in the field of fluid mechanics, numerical simulations. So that's it. Thank you for watching this video. Until the next video, take care of yourselves and bye bye.